I am Mark Freedman. I'm a professor of medicine of neurology at the University of Ottawa and the senior scientist at the Ottawa Hospital Research Institute, and the director of the Multiple Sclerosis Research Clinic at the Ottawa Hospital General Campus. I'm very pleased to be able to present to you today a stem cell update and try to help you to understand the concept of stem cells and appreciate maybe how ready we are for prime time of use of stem cells. This particular recording is accredited, and it's part of the consortium of multiple sclerosis centers and also jointly accredited by the ACCME. This accreditation applies to a number of different groups, including physicians, where the content is good for at least 1 credit, for nurses for 1 contact hour, for pharmacists qualifying also for 1 contact hour, and even for PAs. Psychologists and social workers are not excluded, and they also can claim credit for reviewing this material. I have no disclosures that are pertinent to this particular presentation. I have some learning objectives that hopefully will be met as we go through the content. We'll talk about some of the terminology. Hopefully I'll be able to explain the differences amongst the different sources of stem cells, the uses of these stem cells and the variety of treatments. Spent a lot of time talking especially about hematopoietic stem cells in transplantation for multiple sclerosis, compare some of the results that have been using autologous hematopoietic stem cell transplantation for MS, talk a bit about the mesenchymal stem cell story, and even some of the trials that have been attempting to use mesenchymal stem cells to treat multiple sclerosis. No doubt this is a popular therapy, and unfortunately, where there's money to be had, there is always a concern that a number of centers have preyed upon the promise of stem cell therapy, and people have been seeking out, let's say, inappropriate therapies based only on advertisements and especially on the internet. Dr. Google is very powerful in recommending lots of things that people pay for to go to. Some of these centers have actually been doing a lot of transplantation procedures for patients. Interestingly, an article just last year talked about crowdfunding that was looking to help some of our patients go to some of these places. You can see some of the locations that were on the last slide, such as Stemgenics in the United States, the Clínica Ruiz in Puebla, Mexico, very popular. Even Panama City is probably the #1. But when you look at all the different things that people have crowdfunded for, and we're talking well over 1,000 campaigns, the most common neurological condition that was being looked at was in fact multiple sclerosis, where some 400 people of this group sought crowdfunding to go to attend some of these clinics to get what we would call perhaps unapproved therapies or unproven therapies that these very desperate folks were hopeful for. So this is not a small problem, but trying to distinguish what is a good procedure, a proven procedure, from those that are offering promise for money is the difficulty. So let's talk about some stem cells. What are they? Stem cells themselves are characterized by 2 very important properties, and a third that we are hoping to capitalize on in terms of their abilities for treatment. But the key ability is that these cells have the ability to self-renew, and they still have the full potential to differentiate into many different types of cells. And the terminology is all based on the degree that they can actually differentiate. So as they become differentiated, they lose the capacity to become something to everyone. These renewable source cells have obviously been an issue for almost like future scientific potentials, but you can almost call it sci-fi in some of the stuff in which it's been depicted to do. Like, you cannot clone a person suddenly from one of these cells, but potentially it has the ability to generate any organ. We know that some of these stem cells have the ability to repair, and that's really where we're going with the mesenchymal stem cells, and I'll talk a little bit more about that shortly. So the terminology based on the degree of differentiation as we move from left to right here, that a totipotent stem cell, such as you'd find in the morula stage of the embryogenesis, these cells are all identical, they all have the same kind of programming, and then only after they come this stage where they start to differentiate into the various germ layers that eventually give rise to the various organ systems. But as we go to the right, if you were to take stem cells from, say, a newborn, those cells are not as pluripotential as here. So these are the totipotent. They can be anything. Pluripotent, some restriction. They have the inner cell masses. Multipotent, still able, but not to generate like a full human. And so these terms have been used in various sense to describe the type of stem cells that will be used for treatments. When we talk about the neural stem cells, and these are important because this is where we're hopeful that we'd be able to fix a broken nervous system or repair it, there are a number of sources for neural stem cells. We're nowhere near neuro stem cell transplantation, but there's a lot of literature that really focuses on these four sources, and I'll just briefly touch on them. The embryonic stem cell, which we've heard some debate about, has raised a lot of ethical concerns, as you can imagine, because you'll be deriving these from embryos that are often thrown out as part of a fertilization procedures that are not necessary. We have these very interesting, the pluripotential stem cells that are induced, and these cells can actually be transformed from even an adult fully differentiated cell, and I'll come back to that. That's really almost magical. We still have stem cells even in the adult. We still can get stem cells, especially from olfactory epithelium, believe it or not, but this is not a source of stem cells that we use in humans. And then we can get mesenchymal stem cells, which derive from various body parts. Most commonly, we use the bone marrow, but you can get mesenchymal stem cells from almost any tissue. People have used fatty tissue very commonly, and also I've even seen reports where you can get mesenchymal stem cells from teeth. So all of the various parts of the body have some of those mesenchymal stem cells. When we talk about embryonic stem cells, so these are derived from the embryo, just like I showed you at that stage where the morula occurs. You got the inner cell mass of these embryos, and they can then go into in vitro transformations. They still are very much stem cells. They can self-renew, and they're pluripotent. They're not totipotent, they're pluripotent, but that still allows them to generate just about any tissue of the body, and then even into neural stem cells if you wanted to use them. What everyone forgets is that if you use embryonic stem cells, especially even if it's your own child, we get this question a lot. I'm going to have a baby. Should I save the placenta and get embryonic stem cells from the placenta? Will I be able to use those? Well, even if it's your own child, the best you're going to have as a match is 50% of the DNA. So there's enough mismatch in that embryonic stem cell that if you were to use it for anything other than that person when they grow older, you're going to have a mismatch that you're going to have to deal with. Either the body's going to reject them, or you can get something like graft versus host disease. And it's really important that we keep that in mind. And that's why embryonic stem cells have remained mostly in the laboratory and in use in animals. I guess you can imagine that there's still ethical debate about this, since we are then destroying the embryo in the attempt to try to get these stem cells. I talked about the induced pluripotential stem cells, and this is almost magical. And not surprisingly, that Shinya Yamanaka at the Kyoto University won the Nobel Prize for actually finding this ability, where you can take an adult stem cell and use 4 reprogramming factors that are listed here on the left to retransform these adult cells into a pluripotential stem cell, just like you would find in the embryos. So basically, you're sending that cell that went along a stage of differentiation well back to its origins, at which point those cells can then be sent along the line to become the 3 main layers of an embryo. And we are always interested in the ectoderm because it gives rise to the central nervous system, but the mesoderm gives rise to the entire blood system, the hematopoietic stem cell system. So these have been amazingly productive in the laboratory. For years, if you wanted to work on human neuronal cells or human CNS cells and do experiments with them, you'd have to derive fresh tissue from the brain, or you'd have to culture tissue from the brain. But now you can take even a scraping of the inside of the cheek from a person, perform the IPS reprogramming factors, send those cells along a line, maybe even to differentiate into a neuron, or in the case of multiple sclerosis, an oligodendrocyte, the cell that makes myelin, and do experiments with those cells and maybe even interact them with the immune cells of the same patient. So they're derived from the same person, they all match. Wonderful. Why aren't we using these clinically? They can actually become anything. And the answer is, one of these transforming factors is something called c-MYC, and that is known as an oncogene, and oncogenes cause cancer. So obviously the safety is a big problem here once you've created these iPS cells. But the future is there, and potentially one could get anything from this stem cell depot. These days, probably just with curbside pickup. Sorry about that. Okay, neural stem cells. These cells can be derived from adults. As I suggested to you, they can get them from the olfactory epithelium. We can dissect them from animals. We can grow them in neurospheres. You can get these from human tissue as well. And there have been some phase 1 studies looking at the cells at this neurosphere stage. And theoretically, at least in the Petri dish, one can differentiate these into anything you want. You want neurons, we can make neurons. You want oligodendrocytes, we make oligodendrocytes, no problem. So these cells are absolutely identical to the way the cells form in the body. The problem is, once if you put these back into the body, they don't often do what they're supposed to do because they grew up in a Petri dish. They didn't grow up in the brain. And therein lies the problem. One would hope that if you could just raise a whole bunch of oligodendrocytes and squirt them into MS lesions, that suddenly they will reproduce and start making myelin and laying it down and fix all the problem. But that requires the body's own control. And this is where this particular type of treatment has stalled, because we've not been able to see that cells growing up outside the body behave the way we would want them to once you put them back in the body. And finally, the mesenchymal stem cells. These, I told you, can be derived from many different locations. We typically will use the bone marrow, but a lot of people are doing adipocytes. I mean, there's one center, I think, in India that offers you liposuction in the morning. They get their mesenchymal stem cells and then they inject into you in the afternoon. People are paying a fortune for that. When I get to the mesenchymal stem cell story, it's so clear, it should be clear to you that that's just ridiculous, because the amount of cells that you're going to get in the afternoon from a morning supply of adipocytes is so small that it's likely they'll do very little. In order to get millions and millions of cells that we need for the studies for infusions, you have to culture them, and they have to be cultured in a special facility. But these are very well characterized. They express markers here that probably mean little to you, but their properties allow them to be identified and purified with great purity from the surrounding cells, so you can grow them. Interestingly enough, they don't express the HLA antigens. Those are the mismatch antigens, or the things that we have to match in order to accept a graft. If you were going to get a transplant from somebody or an organ, you'd have to match the HLAs. They don't express them. So in fact, mesenchymal stem cells have been used from one placenta would derive mesenchymal stem cells, for instance, and you can use them on anyone, and they're not rejected because there are no HLA antigens. All right, let's move to stem cell trials in multiple sclerosis, and we'll talk more or less about these two main ones. And I want to point out two things. We use stem cells in bone marrow transplants because without them, people would die. We're removing an old immune system and we're replacing it with a new one. We're removing the old one using chemotherapy. We're removing them so that the cells will die. If we don't have a source of cells to replace the cells that are going to die, the host will die. And that was one of the problems with early on bone marrow transplant trials. We are growing this new immune system from the bone marrow derived stem cells. We don't need to grow any cells. We simply derive the stem cells, freeze them, do the chemotherapy, and then infuse the stem cells. I'm pointing this out to you because people make this mistake all the time. When we talk about the mesenchymal stem cell trials, there is no chemotherapy. We are not removing the old immune system. There's no chemotherapy whatsoever. But in order to get the mesenchymal stem cells in a quantity that's needed for the treatments, we absolutely must culture these cells. So no culture, chemo, no chemo, lots of culture. If you can remember anything else from today, those are the two differentiating features of these particular types of trials. So where are we using them? I think now there's very solid evidence that autologous from yourself, hematopoietic stem cell treatments following a conditioning regimen called bone marrow transplants is an option that we should be considering for multiple sclerosis, and is an option, certainly in Canada and many centers throughout the US and the world are now using this as an option. Mesenchymal stem cell transplantation is not quite there yet. There are a few studies that have been launched and finished.
1 second, I'm going to stop you real quick. Could you just try to make sure your mouse doesn't come onto screen, because the little red dot is a little bit distracting.
Okay, I was using it, but okay.
Thank you.
I'll just go back for a second then. Mesenchymal stem cell transplantation is a different story. It's still at a very early stage. We haven't yet established its efficacy. We have a number of questions that need to be answered, and all we can say from the studies that have been done thus far is that the way in which we're producing these cells and infusing them is probably safe and hasn't created any problems, but we haven't really shown what regimen is best and whether it can truly repair. So let's talk about the hematopoietic stem cells to start with, because this is the one source for both the cells that we're going to use for the transplant and for the culture of the mesenchymal cells. And that's this group here from the bone marrow. You can get this, all the cells you need from this group. You can get all the cells that will give rise to a brand new hematopoietic and immune system, but you can also derive cells that are important for mesenchymal stem cells. Those are over here, but I'll come back to those later. So when we talk about replacement therapy, we're talking about a cell that, just like we were using the terminology at the beginning, we had the multipotent, and we had the totipotent, and we had the pluripotent. These are multipotent. So that means they've already kind of moved along the line to become a blood cell, but they haven't really committed themselves down to becoming a red cell or a white cell. All of that happens after this hematopoietic stem cell comes into the body. You can see they differentiate into the myeloid stem cell system. That gives rise to the bone marrow cells that will eventually come and become monocytes, neutrophils, eosinophils, all the granulocytes here. And then we have the lymphoid stem cell, which differentiates into either T and B lymphocytes, depending, of course, where they end up going. The stem cell goes to the thymus, you get the T cells. If it goes to where the B cells differentiate, then you get the B cells and the plasma cells. Why are we even considering this for multiple sclerosis? What was the rationale? And the idea was, after years of studying MS, nobody could really figure out what the specific immune problem was that was driving the disease. There were many things that were common, But if you looked at individual patients, it may be a different thing operating at a different time. Since we can't figure out what the problem was, maybe if we just literally rebuild the immune system from start, whatever mistake happened along the way, which sequence of viruses or other stimuli to the immune system tripped that particular immune system to recognizing wrongly that myelin was a target and should be destroyed, is unlikely to be repeated. We know that we can completely restore a functional immune system from these stem cells, and we were hoping that this reconstituted system, because it was grown de novo or new and hadn't evolved, is unlikely to start causing disease again. There's also this whole possibility, and this is immunological terminology, where we talk about tolerance. At the time you're reconstituting the immune system, myelin, bits of myelin that had been destroyed already from the early signs of the MS may be around. And so that growing immune system just recognizes that the myelin is part of the body, and that's called tolerance. What we hadn't perceived in the past, and we were wondering if could occur, and certainly was occurring in the animal models, was that these transplanted stem cells, sure, will grow into immune cells, will grow into the hematopoietic system, but for whatever reason, they can also differentiate because they are multipotent to any other organ system. Maybe they can actually become repair cells, and there's some evidence, at least in the animals, that they do this. We've had some tantalizing evidence in the bone marrow transplant studies, because I don't know how else to explain some of this repair, but I'm not going to throw that and say that that's not possible. In order to remove the old immune system, there are two ways of doing this, and this is what we refer to as the conditioning regimens. And the hematologists or the transplant people refer to this as myeloablative or lymphoablative. And what we're referring to with the myeloablative is it's total. You're knocking out the entire bone marrow. You're removing everything, because if you don't remove everything, whatever that abnormality was that caused the disease to begin with still may be living in the bone marrow itself. Whereas lymphoablative says, well, we'll spare the bone marrow, and that usually means it's a less toxic regimen. And we'll remove the cells that have made it out of the bone marrow. We'll just remove those, and hopefully there aren't any bad guys hiding around in the bone marrow. Obviously, myeloablatives are going to be more potent conditioning regimens, and with that comes more risk and safety issues, whereas lymphoablative is thought to be able to spare some of the bone marrow cells, but at the same time, both of these procedures are probably not ones that you would want to do more than once in a lifetime. And when you see the results of some of the studies and the different conditioning regimens, you'll understand where our rationale comes from. So where are we going to use this? Patients have come from all over, and believe it or not, some people have shown up even after one attack, say, oh, I have MS. I heard that bone marrow transplant will cure this disease. So let's go for the bone marrow transplant now. I don't want to have to deal with this the rest of my life. I guess I can understand that kind of concept, but at the same time, this is a horrendous procedure. And because it still has risk, although it's much smaller today than it was years ago, there's a risk of a very serious complication, including death. So we typically will reserve it for patients who show up with a lot more of an aggressive type of disease. What we don't want it to become is a treatment of last resort. You don't want to try absolutely everything in your tool chest, and only after the patient has become so disabled in a wheelchair, they go, oh, okay, let's do a transplant, because it's not going to do anything for those patients. It's for people who have raging disease that we simply cannot control with today's approved therapies. And there is a small contingent of patients that have that type of aggressive MS, probably no more than 5 or 10% of all the patients we see today. There have been a number of phase 2 trials. There have even been some phase 3s, but they're questionable phase 3s. But phase 2 trials where we've been able to see that the immunoablative, that less powerful regimen of conditioning, has led to less morbidity, but you're sacrificing less morbidity or more safety, but less than 100% disease control. And that's only over 2 years. If you went out 5 or 10 years, it's actually much less control. The myeloablative procedures have established much better disease control, although the morbidity is slightly higher. The other sort of covariant in this whole ability to do bone marrow transplants is this question of, should you be doing a separation, a cell separation or a cell selection? And this is what refers to as the CD4 selection. So CD34 marks a stem cell. So you don't have to do this. And a lot of centers will avoid it because it's costly and they often don't have a facility to do this. We're fortunate in Canada where we do these, this is all done for us by Canadian Blood Services. And what this technique does, it's no different than what we do in the lab, is you take these little antibodies that are hooked onto an iron molecule, as you can see here, and they are reactive to CD34. So if you're a stem cell that has CD34 on the surface, you're going to get tagged with this antibody that's got a little iron piece on it. This cell is not. And what happens then is you throw the whole mixture into a tube, and it sits into this column, and this is a big magnet. So we're just sort of cartoon on the side here. This is the actual machine. And this magnet then, as the cells go through the column, the magnet will hold back all the stem cells because there's this little iron piece that's holding on to it. Anything that's not a stem cell will go through. So you can see the color is the same down here. And then after you dump these cells and take a fresh tube, you release the magnet, and all the cells that had this antibody on it then fall to the bottom. And so you now have purified CD34 positive stem cells that are important for 2 reasons. One, there's an enriched group of stem cells, so grafting becomes very easy, although that's not much of an issue without the selection. But we think that the importance of this step is that in amongst these cells that are not stem cells are probably those cells that may well be capable of causing the disease again. So although it's a positive selection for stem cells, it's also a negative selection in that you're eliminating any cell that might have the ability to cause disease again. So this negative selection actually purifies down the cells, and we are probably looking at giving back a very pure set of cells that can reconstitute the immune system, but not cause disease again. And that's exactly what we did in the Canadian bone marrow transplant study. So I'll just tell you briefly about it because it's been out now for several years. This was a small study. There was uncontrolled patients with aggressive forms of MS. We did 24 patients. They were very, very active. About half were secondary progressive, as you can see here. The other half relapsing. And they had very short duration MS. Look, mean 4.1 years to EDSS3. So they did not have disease for a very long time. And they had all been tried on various therapies before going into the study. The importance here is that some of the studies have focused only on relapsing, some have only focused on secondary progressive, and I'll review that for you very shortly. When we look at the kinds of treatments they've had on the left, you can see they've all had at least one, some have had even 3 lines of treatments. The EDSS scores were shown here on the right. So you see most of the patients here were already at a very high level disability at EDSS 6. You couldn't get in under 3, so that represents this. And you couldn't come in if you were more than 6. So if you're already walking with a walker, it was too late to get into this trial. And the results, I'll just briefly show you here and walk you through this because it's a busy slide. Every one of these lines represents a patient. The vertical line down the center here is the time when we did the transplant. The little triangles here before this time period represents relapses that they've had. So you can see a very high relapsing population. And the vertical bar here gives you the time course from the beginning of their symptoms to when they became an EDSS of 3. So you get some idea of how active these patients were prior to the transplant. And then if you look to the right here, no relapses. at all. And we follow these patients now out. Our first patient was done in the turn of the century. So we're looking at 20 years of follow-up and nobody's had a relapse yet. And that's pretty well shown here. Lots of relapses before, a high attack rate, about 3 to 4 times what you would see in most clinical studies today. Post-transplant, 0. What about the MRIs? Similar type of graph. Here's the bone marrow transplant at time 0. The little black things here along each line representing a patient represents the timing of an MRI. And the triangles here represent MRIs that had been done prior to the transplant that had activity. So very active MRIs coming in since the transplant. Not a single new lesion has been seen in anybody going out now 20 years. So how fast were these patients moving coming in? You can see this time trajectory to when they became EDSS3 or EDSS6. It did not take them a long time. So these are truly aggressive patients. And I just want you to focus in on this curve because this is really important. You'll notice here that this is progression. So this is EDSS progression, and here's the transplant. But some patients continued to progress for about 18 months. But after 18 months, there were no more progressions. So all of that happened up front. And that's indifferent to some of the studies I'm going to show you later, where you don't get this leveling off, you get continued growth. And that means people falling off the curve and continuing to progress. And we think this represents probably something that we couldn't change, because the inflammation that the patients have and brought to the table with the transplant, that probably kick-started some kind of a process that leads to the progression, that even if you stop the inflammation cold, as we do with the bone marrow transplant, whatever started before is going to sort of pan out. We haven't stopped that process, and it reaches its peak here, and then we don't see it anymore. We've had something else that we didn't anticipate, and that is this improvement. But not surprisingly, we've seen this with drugs like alemtuzumab, that if you can stop enough of the inflammation, you get patients starting to improve. But we did not expect to see this kind of improvement continue, and well beyond where you started to see the progression level off. So this is where I sort of threw out that tantalizing possibility that maybe those stem cells that are going in and reconstituting the immune system, maybe they might be doing something else. Maybe it's more than just facilitating the repair of the natural repair of the body, but there is some evidence these stem cells could differentiate into cells that could go into the brain and not repair themselves, but the evidence would suggest that at least they may wake up whatever repair systems there are that were dormant and now can function to repair the central nervous system. We also looked at atrophy, and I'm going to walk you through this very busy diagram. So people are very concerned about brain atrophy. We just published an article showing why in the second 6 months, from 0 to 6 months, this is baseline, but look at all the atrophy that's occurring in the first year. And we think this is due to the conditioning regimen, especially the one that we use called busulfan. But let me introduce you to this slide. So this gray line here is unfortunately the degree of atrophy that we all suffer, whether you have MS or not. That's normal aging, loss of brain tissue. MS patients that are untreated lose brain a lot faster than the normals. And that's this gray sort of wide bar here, which are the confidence limits. The average of about 0.4% to 0.6% of brain per year, which is about 4 to 5 times what the natural population will have. So this is where an untreated patient would be. This would be a normal. And you can see that our population coming in at the beginning was losing brain at the same rate as an untreated MS patient. So they're really not well treated. Then after the transplant, they have this accelerated brain atrophy that only occurs in the first 6 months, feature of the busulfan probably toxicity, because we're using a regimen of chemo that gets into the central nervous system. That's what we wanted to do. We wanted to get these drugs into the central nervous system to destroy the cells that might be leading to the damage that causes MS. So if you can't get those immune cells out, then what are we doing? So that's why we chose those drugs. In the second 6 months, atrophy is almost zero, and in fact, less than what you would see with normal aging. By the second year, the atrophy comes back. So here's the completion of the bone marrow transplant, and this is month 12 to month 24. Very discouraging. We saw atrophy at the same rate they had at the baseline, but we continued to follow these patients, and as the new system built in, and around the same time, we started to see all that recovery and the repair that we thought may have been going on. We are seeing the diminishing rate of atrophy. By the time we're getting out here to 5 years, patients are losing brain at the same rate as normal age-matched controls. And that has continued now for years. And so this was very encouraging. Everyone's very interested in this new thing called serum neurofilament light. So we just finished our review of our bone marrow transplant group, and we published this, as you can see at the bottom. We have noted, similar to other people, that patients with very high levels of neurofilaments, serum neurofilaments, represent a very high disabled group. As you can see here, the group that was 6 or more at the beginning had a much higher level than the group that was less than 6. Interestingly, the patients that changed, that got worse on their EDSS and progressed, had the highest levels of neurofilament. And if you just cut the level at 30 picograms per ml, this is the median in our group, patients whose neurofilament level was above the median did worse, this is their EDSS, and those below the median did better. And if you looked at it as a predictor, the group at the highest actually were the ones could have been predicted to get worse, whereas those that had lower levels, you can see the levels dropped off by every year, and those patients had actually recovered, and their EDSS went down with time. And that's just showing here a little bit more dramatically, but also correlating with, so there's the EDSS, the same diagram from the last. Those that had low neurofilaments actually improved their EDSS. Those with higher levels tended to get worse, and that was mirrored by T1 black holes that are shown here, T2 lesion loads that decreased in one group and continued in another group, and even this study called MRS, which looked at the neuronal integrity. So now the patients who had the lowest neurofilament level had the greatest improvement in NAA, which represents neuronal integrity. So we think the neurofilaments can actually help us, and we've seen this correlation now in a number of areas, but in particular, when we separated the gray and the white matter, you can see that where the atrophy is occurring, there's a much more atrophic looking white matter in patients that had very high neurofilament levels. And the gray atrophy was very much protected by this. So there may be another factor that you could consider before going into bone marrow transplant is your level of neurofilaments, and that could be a predictor of how well you will do. This recently published study from the Italians looked at their regimen of a lymphoablative treatment. This was the recommended beam therapy from the European Bone Marrow Transplant Group. And I just throw this in here because you can see here that these patients did worse. And so in general, this was 100% of patients with secondary progressive MS. Look what happened here from relapses, same results as we've had, no further relapses going out to 10 years. That's seen here. And here's MRI activity, it's very similar to us. No MRI activity going out to 10 years, but almost 50% of the patients progressed. And there was continued progression out here. So their recommendation is that there's a very small subset of secondary progressive MS, and probably we need to get to these patients earlier. Interestingly, they looked at some of the progression that was occurring, and there's one thing they called one-step progressions. That means they only had one change in the EDSS, where those had continuous disease activity. That's over here. But there are a lot of people who had just one-step progression, almost similar to what I showed you, where had this little bit of progression, and then they leveled off, and they were starting to see a bit of that. And it may well be that that represents something that has happened prior to them coming into the study. They had the same deduction as we did from that progressive line. So in summary, from bone marrow transplantations, we can see that these regimens are very powerful. They stop inflammation cold. They can really stop further damage from occurring, and we see, at least in some cases, some recovery of disability. And oh, I guess I forgot to mention this. Bottom line here is these patients don't need to be treated with anything else. They are not followed with any disease-modifying drug. So most of the studies are talking about cost effectiveness. Depending on the upfront cost for these various treatments, and it depends where in the world you're doing it. In Canada, for instance, the entire cost of procedure is some 40,000 Canadian dollars. I've seen numbers in the United States of upwards of $120,000. But once you finish the transplant, that's it. You don't have to take disease-modifying drugs anymore because there's no more inflammation that's driving the disease in the majority of these patients. And that represents a huge cost saving to the individual and to who's ever paying for these. So the same Italian author, in conjunction with Paolo Moraro in the UK, summarized the various studies. Here's ours over here. Richard Burt published one in 2015, another more recently. This NASH study here is which one? I can't remember. This is, they had a nickname for it in the United States, I can't remember, but it was the American study. And then there were two other ones here, but my point is to look at a few things on this slide. So the green is EDSS improvements, the red is worsening, and the yellow is stabilization. So everybody sees improvement. Depends on various studies, looked at different groups, but they all see some improvements. Most, except for one study, saw some deterioration. This was the Scandinavian group by Jan Berman's group, and the difference here is 100% of these patients are relapsing MS. No secondary progressives. We had half of our patients secondary progressive. The little round circle here, this is important because this is the level of conditioning. So the highly myeloablative procedure that we used is shown here. Others have used low levels or medium levels of conditioning and got different results. The one you should look at here is progression-free survival, and that's the little triangle that you see here. So in this group here, more of these patients had progression-free survival. We had about 70% here. Some groups did better, but at what cost? So NIDA is no evidence of disease activity whatsoever. The circle here is relapse-free survival. The only one that's 100% relapse-free is ours. The others, 20 to 30%, depending on which group, continue to have relapses, which means these patients still have activity and they probably need some kind of treatment going forward. When we look at the selection of the CD34s, so ours was a selected one, the unselected one was here, this was also selected. These curves continue down, see this one continues down, ours levels off. Is it the selection that makes a difference? We don't know, nobody's tried to compare selected, that's the CD34 selection versus not. We think that this maybe is a procedure that helps to get rid of all the potential offending cells that are left in the graft. And we're reluctant to give that up. When we look at this again, this is the review of the trials here. Here's, for reference, some of the high efficacy therapies. The Sentinel trial and AFFIRM used natalizumab. The CARE-MS trials used alemtuzumab. The OPERA studies uses ocrelizumab. Here are the 4 different treatment trials that looked at pre-treatment relapse rates. You can see going in here, very high relapse rate in the Scandinavian group. Post-treatments, almost nothing, or a little bit, nothing. That's ours over here. But compared to the best disease-modifying medication, all of these continue to allow relapses to occur. So I think from a relapse rate standpoint, there's no question that AHST is superior, and every study has shown that. When we look at which kind of patient may be best for this, there are a number of factors. So obviously, more relapses at the beginning, so more of a relapsing population is going to do better than those who are progressive. And the younger patients, younger versus old, are going to do better. And this is probably intuitive, but that's what the entire bone marrow transplant registry has shown us over the years. What are we doing different in Ottawa? Well, our trial was really driven by the MS Society grant that we had to do this. And so we had a very strict set of rules for the patients that came in. But clearly what we've learned from this is that we could probably widen these inclusion criteria. And now we tend to get patients, we're kind of trying to still head for under 50 years, because above the age of 50, there's more complications from the procedure. That's kind of one of the reasons. Also, there's less of a chance of that highly inflammatory component that's the target of the bone marrow transplant from being dominant. We're looking for aggressive early disease, but we're a little more relaxed in the number of attacks. We want to see that these attacks are meaningful, that they're already starting to show some damage in the patient, but not to the point where they're already acquired significant disability. And we're looking for activity. It could be in the form of relapses or on MRI, but usually the MRI is already active. And importantly, they can't have some other significant comorbidity like kidney failure or other entity that would make it difficult for us to get through without a safety issue. So I think in conclusion, this is an option that we could use for very aggressive patients. I think it's really important to look at the conditioning regimen. That's the kind of thing that really drives the end result. We see this delayed recovery. I don't know, is it just that we've gotten rid of the inflammation, the patients have an innate ability to repair and they're repairing better in the absence of ongoing inflammation? Or are these cells really doing something? Is there something positive that they're stimulating? It's very possible. And I think as we move forward, we're going to bring in more tools to help us predict response, such as a biomarker like neurofilament lights. So now let's move on and briefly talk about this group of cells, the mesenchymal stem cells that I told you can get from a number of different places, even fat cells, but typically the bone marrow. What's of interest is these cells almost look like fibroblasts when you culture them, but they're very unique. You can see them. They can differentiate just because they are totipotent. They can give rise to all three germ layers. Remember, the ectoderm is the one that gives rise to the nervous system. That's this group over here. But we can get, and we can show that these mesenchymal stem cells can become anything. In reality, they don't. But this is one of the things that they were hopeful for, especially there are some conditions such as osteogenesis imperfecta, a genetic disorder in children where they don't get the bone-forming cells. They can actually get these from mesenchymal stem cells, and that's the kind of trials that they're being used for outside of where we're studying them. There are tons of things that these mesenchymal stem cells do, and there's a lot of terminology and jargon here, and don't worry about all little arrows going everywhere, but the point is these cells are capable of manipulating and controlling the immune system, and they have many, many, many types of things that they can release to either stimulate or retard immune reactions, depending on where they are and what the reaction is. And that's what makes them unique. They are attracted to sites of damage in the body. And when they get there, depending on what is driving the damage, they have the capacity to release whatever may be necessary to take care of damage in that area. They have been studied in a number of different things. As you can see here on the left, a whole list of autoimmune diseases where mesenchymal stem cells have been looked at. Multiple sclerosis here is in orange, so certainly not a small group that they've been studied in. Graft versus host disease is kind of where this all came from in attempts to try to control inflammation that was rejecting bone marrow transplant, life-saving bone marrow transplant grafts that would have killed, the disease would have killed these children in the absence of these mesenchymal stem cells. But You can see all the different studies that are going on. And where do they get them from? Bone marrow is still number one, but you can get them from anywhere. 19% or so have been taken from tissue and umbilical cells. So adipocytes, this is fat cells, this is umbilical cells from placenta, but there are many, many different sources. Even gingiva in your in your gums, you can give rise to mesenchymal stem cells. And I don't expect you to read this, but I expect you to see maybe the main titles. And these are why we are doing these trials, because the stem cells have the capacity, and all these little in the fine print here, this is where all the evidence is, that they can remyelinate in certain animal models. We can see the reduction of glial scars that may be retarding myelin repair. They can, in some cases, induce the formation of new blood vessels, hence the angiogenesis. Probably the main thing that we can prove maybe is that they can suppress inflammation and cause some immune modulation. This is what we would hope to be able to prove in our studies. We'd love to see neuroprotection. We have models where that works in this sense in the animals. And probably the least likely, but it's still, there's evidence for it, is that the cells can actually fuse with the body's own cells and redirect them. So if you've got a cell like a microglial cell that's sitting in the brain, is not doing what it's supposed to do, it could possibly fuse with a mesenchymal stem cell and now wake up and get redirected to actually repair when it wasn't doing that before. So all of this has been done in the animals, and the evidence is clearly there for it. So we launched this big trial that just we reported for the first time last fall. Joint efforts in many different countries, as you can see here, to try to see if we could get mesenchymal stem cells given intravenously to do anything into our patients. It was a phase 2A study. The Canadian arm was called MESCAMS as opposed to MESMS. And it was a 24-week crossover study. So patients didn't know whether they got their cells at the beginning, but we knew that they were going to get their cells at 6 months. And then we followed the group over the ensuing 6 months. All of this funded by individual MS societies throughout the world. Really a formidable task. Then the big step is to get these cells and get them growing. And this is what I told you at the very beginning, differentiates it from bone marrow transplants. You got to get the cells out. You need a specialized facility. This is ours here. You can see these are not technically small devices. They're special cultured rooms. They are negative pressure rooms. They are very, very carefully regulated for the growth of human cells. You have one pathogen in there, it shuts down the lab. So very strict criteria for the release of the cells. In fact, we couldn't give these cells to any patient without faxing technical data to Health Canada, and only upon their reply that, yes, you can go ahead and give the cells to patients, could we actually move forward. And there are similar, not identical, but similar kinds of restrictive protocols throughout the world, and we were all guided by whatever our national policy was. When we look at the kinds of cells that we derived, and this is just our group here, we looked at that these cells were nucleated. So this is some of the quality control that we were doing for our patients to make sure that what we were growing were in fact mesenchymal stem cells. And you can see some of those features here. We looked at these types of technical aspects, and this is what was faxed to Health Canada to assure us that we had a product that truly was mesenchymal stem cells. And what we were hoping to show is that there is some biological effect of these cells. Now, if I said, oh, let's just put them in and repair MS, you'd go, well, why didn't you do that? I go, well, okay, how do I measure repair? How do we measure repair? How can we be convinced that when we put something in, short of somebody arising from a wheelchair that they've never done that before, I mean, we need to be able to have a marker of repair, and we don't have such an animal. So we went after something that we thought we could do, which was one of the features of these cells is to reduce inflammation. So we looked at whether or not the infusion of these cells could reduce the number of enhancing lesions. This is what's been done for just about every therapy we have today for treatment of MS. Why can't we do it with the mesenchymal stem cells? So this is what we looked at. We looked at a number of other features and all these exploratory measures in the hope that we could see something in the way of neuroprotection or repair. This is the design of the study. So the patients either went to arm 1 or arm 2. They got cells. They were not really cells. They were more cultural media. We called it the mass control. But eventually at month 24, whatever they didn't get, if they didn't get their cells here, they got them here. So everybody got cells at some point. And the primary endpoint was at 6 months. And this is our numbers. These were presented last year at the ECTRIMS meeting in Stockholm. And so this is the end of the first phase where they get their first infusion. And then this is 6 months here, and we followed them for a year. We reported out on the 6 months. Baseline characteristics were all over the place because we had relapsing, remitting, secondary progressive, and primary progressive. And it didn't matter. As long as they had an enhancing lesion in the last year, they got in. And so, many of them actually had enhancing lesions even at baseline. But that was our outcome measure. So we wanted to be sure that they had something that we could actually look at. There were 2 primary aims. One is the safety, since this is a multi-center study, everybody doing their own thing under the guise of this consortium that we put together to run this trial. They were all trying to raise the product the similar way, but guided by national restrictions. So we wanted to know that it was safe, and we wanted to know if we could measure something in the way of not only adverse events, but hopefully reduction of new activity. So the adverse events were very small. In fact, these were intravenously given cells, large volume of cells in one infusion, and there's nothing here that I would have to say is of any kind of concern. I think even the grade 4 event here was, I think, a seizure in a patient that required them to be in hospital. So very, very few events whatsoever of concern. Unfortunately, when it came to the primary endpoint at 6 months, we saw very little in the way of an effect. In fact, there's no statistical difference here, although the lines look a little different here. So we could not see, but we did see this, and we were very intrigued by it. Now, there's more analysis going on here, but when we looked at relapses, now remember, only a small proportion of patients in this study were relapsing patients, but there was a trend, a very important trend, in favor of the mesenchymal stem cells. So a lot more analysis going on now with the primary center right now in Genoa, Italy. I don't need to tell you that they have some other things on their mind right now, and they haven't been able to focus their attention on completing a lot of the analysis, but it is happening. Other groups have done this in small centers and reported similar kinds of results. Jeff Cohen in the United States showed a while ago that this is a safe procedure to do. The Israelis have looked at this for years and shown it's a safe to put these cells in, but nobody's given us convincing data that they're actually repairing. So we know they're safe. At least in our study, we haven't seen them turn down inflammatory lesions. Quite honestly, that's not what we wanted. If these cells can't repair, we've got other treatments that could reduce inflammatory lesions. What we're hoping to do now in the final analysis is say, using that maybe the relapse rate reduction or some new MRI data that hasn't yet been shown, but that may show a reduction in T2 lesion, we could call these patients a responder versus a non-responder. We'll see if we can see anything in terms of repair, because we've got a whole bunch of other things that we looked at, and that information will be coming. We know that there's some potency, so one of the questions could be, how do you know that the cells you put in actually are capable of turning down inflammation? A reasonable question. Maybe you're culturing cells that look something, but they don't have any activity. And so we looked at the Ottawa and Winnipeg patients, that's the Canadian group, and we measured something called IDO, which is something that shows that these cells are capable of reducing inflammation. And we can see that these cells are making lots of this stuff. So I know that they're biologically active cells, but we don't know if certain patients are more likely to respond than others. So let me conclude there with, in general, I hope I've addressed a lot of the objectives, but we're very intrigued by stem cells. The biology is still being worked out. We have many sources available to us that need to be very strictly controlled, and we need to establish their safety. I think for autologous hematopoietic stem cell treatments, this is now considered an option for patients who have very much aggressive disease, and we can show that the various regimens can restore a very high functioning immunological system and possibly one that can repair. We have been able to source mesenchymal stem cells. We know they have a huge potential. We are yet to get the data that helps us know what's the best source, how much do you need, how often do you have to give them, and more importantly, let's get some data that show that they actually repair. And in the sci-fi future, maybe we can establish that induced pluripotential stem cells are safe, but right now they're not. We know they have a huge potential because they can become any cell of the body, but getting those cells to do what they're supposed to do when they get into the body, that's another story. You know, we've known about insulin for years in diabetes. We can make an insulin-making cell out of an iPSC, but when you put them into the pancreas, they don't do what they're supposed to do because they didn't grow up in the pancreas. So we've got some room to go, and I think the future is very, very hopeful for everyone. But for now, I would have to say hematopoietic stem cell treatments, that would be mainstream. Mesenchymal stem cell, very much a research tool. And thank you very much for your attention today. This cannot be done without acknowledging a number of people who have been involved, not only in our own center, as you see here, but throughout the world to help us with the bone marrow transplants. This work with the mesenchymal stem cells would not have been possible without the coordinated efforts of all the different groups you see here, including the consortium that helped us put together the original group to conceive of the mesenchymal stem cell transplantation. So once again, thank you for your attention.